Continuing our series of regressions, our next topic is exponential regressions. Again, what is an exponential regression? We have to do regressions when we have data that we believe forms a specific type of function, in this case an exponential function. And we look at it, we plot the points, and we see that, this looks like an exponential graph, but the data doesn't necessarily look perfectly exponential. If that's the case, then we need to do a regression to find out what's the closest graph we can get to fit that. Now sometimes when we do a regression we may get a perfect graph, but most of the time it will not be a perfect graph, and we will have to look for the one that is the best fit. Let's look at an example. A city grows exponentially over the course of time. The table below represents the population during a 50-year period. So from 1950 to 2000, it grew from 12,000 to 15,000 to 20,000, 26,000, 35,000, and 44,000. Again, just like we did in our earlier example, we did not want to plug in years. So we're going to set 1950 as year 0. That means 1960 is year 10, 70s 20, 80s 30, 90s 40, and the year 2000 is the year 50. Again, all we're doing is measuring from 1950. Our population will stay the same. Find an exponential function which shows how the population depends on time. Extrapolate the city's population in the year 2008. Identify the meaning of A and B in the model, and how good of a fit is this model. Let's talk about what we need to do when we talk about finding an exponential function which shows how population depends on time. Again, since population depends on time, the time is the x variable, and population is the y variable. Here's another link to the applet. We're looking for a function f of x equals a times b to the x. So we're going to click on our link. This will pull us up to the exponential regression applet. Let's look back at our data. Our x values are 0, 10, 20, 30, 40, and 50. And our y values are 12, 15, 20, 26, 35, and 44. When we plot this kind of looks quadratic, but it's also, typically when you're dealing with growth, such as growth in cities, or decay or shrinking in populations, those are always exponential graphs, not quadratics. If we go to analyze this, we get A is 11.7837 and B is 1.0269. Notice the correlation coefficient is 0.9992. This is a very strong correlation again. To answer our first question, our f of x was 11.7837 times the quantity 1.0269x to the x power. That is our model. We asked to extrapolate again, go outside our data range, and find the city's population in year 2008. Well, 2008 is 58 years since 1950. So we'll plug in 58 into our function, and we wind up with 54.9433. So in 2008, the population will be approximately 55,000 for the city. Identify the meaning of A and B in the model. We were given the equation f of x equals 11.7837 times the quantity 1.0269. A is 11.7837. This is the beginning point of our data, or the initial population. If we go back to our data, it says the beginning point is 12. Again, the model is our best approximation, so it's very close to what the actual measured data point is. Now B is 1.0269. This is called our compounding factor. And by definition, B equals 1 plus R, where R is the rate of growth. In this case, R is simply 0.0269. Now typically when we talk about rates, we talk about percent. So if I write R as a percent, it's 2.69%, which means the city is growing at 2.69% per year. And the last question was, how good of a fit is this model? We already discussed how the correlation coefficient was 0.9992. That's very close to 1, so again, this is a very strong or very good fit for our model.